lower level optimization problem, and therefore this is a bilevel optimization problem. Similarly, there might be optimization problems which have equilibrium satisfaction as a constraint. Let's say in a chemical industry, if there is some kind of a reaction going on within a reactor, and you have fed in some reactants within the system, then the thing is that for whatever quantity of reactants you have fed into the system, you would like to wait until the system gets into the equilibrium. And once the system is in equilibrium, then you get to know what is the output of the product. What is the output of the system? What is the product? So for any amount of reactants what you are choosing, you have to wait until the system optimizes itself and the product is produced. Therefore, there is a lower level or a nested optimization task going on. If at all you convert this problem into a mathematical optimization problem, then finding the equilibrium itself is a lower level task or an inner level optimization task which you need to solve every time. Similarly, in design, you might like to satisfy the stability of the system. So whatever design variables you choose, you would like your system to be stable. And then, if at all you would like to modify the design, you go with different set of design variables. Again, make sure that the system is stable, and that's how you keep on changing the design until it is optimized. So you want to optimize the design, but for whatever variables you choose, you also need to ascertain that the system is stable. So these things appear as a lower level optimization task, and the feasibility in all these problems is determined only after solving the nested task. In Stackelberg games, what happens is, I already mentioned there is a leader and a follower. So the leader is the person who makes the first move, and then the follower is the person who reacts rationally and then makes its move. If I can take a simple example, it would be more like a tic-tac-toe game, though it's not a very good example of a bilevel problem, but just to give you an initial idea. As a leader, if I just consider the person who's starting the game, if I call him the leader, then he needs to put the cross in the right box, and he has the command. And if in a simple 3x3 tic-tac-toe game, you can ensure right from the beginning by making the right moves that you would never lose. Right? So you as a leader have a higher control over the game, and the follower has lesser control. So if as a leader you are making the right moves, you will never lose. And the same goes on for the follower as well, but the follower would never win. A real-world example from the field of economics is a hierarchical decision-making task where there is a leader who's the owner of a company, and he dictates the selling price and supply. So let's say if I'm the owner of a company and I'm manufacturing some goods, I can always determine how much to supply. I can always assume that I need to supply this much quantity of the product, as well as this should be the price. But is the chosen quantity and is the chosen price good? I don't know. I need to optimize the buyer's problem. So whatever quantity I supply and whatever price tag I put on the product, the lower level problem needs to be optimized, which is the customers optimizing their own utility. If the customers feel that the product is very costly, nobody will buy your product. Therefore, as the leader of the company, you need to look into the followers' problem as well, and you have to anticipate the response of the followers in order to maximize your overall profit. I've presented a simple linear optimization problem here. It's not bilevel. It's a simple linear optimization task. Now the way we'll just put it on a graph here and see where the solution to this optimization problem lies. So we have the two variables x and y, and we have the objective function f, and we have shown a direction in which you need to move in order to minimize the value of the function. Now I just plot the constraints over here. Now once the constraints are plotted, we find that this is the feasible region. Now in this feasible region, the optimal solution to the problem is given by this point, because that's where the value of the function gets minimized. Now let's move on and let's put all the constraints into a lower level optimization task. So what we have done is we have added all the constraints into the lower level optimization task, and we have added one more objective over here. Now the problem here is you have to minimize this subject to y should always be a minimum solution to this optimization problem. Let's see how it looks graphically. Now this was the feasible space, this is the feasible space for the lower level problem. And if at all I pick up, that's the direction in which you need to move in order to minimize the lower level objective function. Now if at all I choose one particular upper level variable which is x1, then the optimal solution to the lower level problem is this, if I fix x1, right? Similarly, if I fix another upper level variable which is x2, then the optimal solution to this is this. Therefore, these become optimal solutions to the lower level problem. Now, what are all the possible optimal solutions for the lower level problem? It's represented by these two lines, right? So this particular set of points become feasible members for the upper level problem. Now, once these are feasible members, then the upper level objective function is minimized in this direction, and then the solution to the bi-level problem is this. Therefore, we see that this differs from the solution we would have got by simply optimizing the upper level variable, upper level objective function in the absence of the lower level problem. But if at all the lower level problem is present, the optimal solution entirely changes. Some of the properties of the bi-level problems are listed over here. So these are non-convex, disconnected, and strongly NP-hard problems, much harder than a normal optimization problem. And the only reason is that even to determine feasibility, every time you have to solve a lower level optimization problem, which itself could be very difficult and time-taking. And then, if at all you are having multiple global solutions at the lower level, so you don't have a single solution to the optimization problem at the lower level, but if at all there are multiple solutions, then the problem becomes even more harder to handle, because you need to figure out all the optimal solutions for the lower level problem in order to make any decision at the upper level. And then the two objectives or the two levels can be cooperating or conflicting. If at all there is a conflict, that adds another flavor of difficulty to the overall optimization problem. Now these problems are not anywhere close to multi-objective problems. They are very different. Somebody might confuse that, okay, these problems also have two objectives, so there might be some kind of similarity with the bi-level and multi-objective optimization problems, but actually it's not. And that's something I'll try to show through a simple example, that if at all we consider both the objectives from the bi-level problem, we consider over here, and we formulate the problem as a multi-objective problem, and I plot the Pareto optimal solution, it is this. So just remember, this is the decision space, that's why the frontier looks like this. So this is the Pareto optimal solution to this multi-objective problem, but the bi-level optimum is over here. Therefore, what we can say is that though both the problems involve two objectives, a bi-level solution is not necessarily one of the Pareto optimal solutions. Moreover, multi-objective problems usually have multiple optimal solutions, and bi-level optimization problems usually have a single optimal solution. And it's not possible at all to use directly one of the multi-objective optimization algorithms to solve bi-level problems. Some of the solution methodologies which people have used to handle bi-level problems are listed here. Like, they either take an approximation of the lower level problem and then completely eliminate the lower level optimization task. So for every upper level variable x, they assume that, okay, this is the function which determines the lower level optimal variable, and completely remove the lower level optimization task, making it a simple optimization problem. Some of the people, they just replace the lower level optimization problem with the KKT conditions, so an additional constraint appears in the lower level task, and that's how they solve the problem. Some even discretize the bi-level problem and then use a nested strategy. A nested strategy is something like when you consider a particular upper level variable and then you completely solve the lower level problem for that particular upper level variable. And you go on doing that for each and every variable until and unless you converge to one of the solutions. People have also used penalty-based approaches, but these are valid only for very special kind of bi-level problems, not for all. Now I'll list down some of the applications which would probably make it easier for you to understand, because this in itself is not a very easy concept and it might be very difficult to grasp things in an hour or so. So probably the application examples might be helpful. Let's assume a toll setting problem where there is an authority and then there are highway users. So the authority wants to maximize its revenues earned from the toll. Now whatever toll prices it sets for the highways, what the users are going to do is they will optimize their own travel costs. So they might have a few objectives, like they would like to minimize cost, they would also think of time, and then they might see that, okay, the highway is a bit too costly for me, so maybe I'll not even take the highway, even though it's a very nice one and the government has recently constructed it. Therefore, if at all the government wants to maximize its own revenues, it needs to take into account the highway users as well, and for any toll it sets, it would like to optimize the lower level problem and see how many users are using it. Is the government are they getting the maximum revenues out of it or not? Or maybe they would like to lower the toll prices a bit in order to get the maximum revenues. Similarly, in a hierarchical setting, as I already mentioned, there could be an owner of a company who dictates the selling price and the supply, and he would like to maximize his profit. Now he needs to anticipate the function which the buyers are optimizing. The buyers might optimize their own utility, and based on that, either they will be buying the product or they will be not. Therefore, for any price which the seller sets, he needs to take care of the optimization problem of the lower level guys in order to maximize his own profit. There is this recent example on which we started working on, and there is this Kuusamo region in Finland, which is a very beautiful skiing resort. It's a summer resort as well, and people go there for rafting and all such kind of things. There's a beautiful river, and there's a nice slope for skiing. Now, this place has another good thing to it. It has enormous amount of gold in it. So there are some mining companies who are really interested in extracting the gold which is present there in that region. And of course, the government also sees that there is enormous cash available over there. But now the problem is that if at all the mining companies do the mining and extract gold from that region, the place would no longer be environmentally that beautiful. Therefore, the government has a couple of objectives. It would of course like to maximize its revenues, which it would be earning from the mining companies, but then at the same time, it would like to minimize the pollution which the mining companies are causing. So whatever taxes the government decides, whatever taxes or whatever constraints the government sets for the mining companies, what the mining companies are going to do is, they will try to optimize their own profit within the constraints set by the government. Now it's the government or the leader's problem that what kind of constraints the government should set so that the government's revenues are maximized as well as the pollution is minimized. So you can see a hierarchy over here, that there is a leader who would like to maximize his profit, but at the same time, he would like to take into consideration the optimization problem of the lower level or optimization problem of the follower, so that whatever solution the leader comes up with is actually really good for him. Actually, we collected some data and we went on to solve this problem. And here, I haven't showed all the results, but I've just shown the final front here. If at all there are 4 technologies available for the mining company, then the government would solve the overall optimization problem, and it would generate a frontier like this. The x-axis represents the revenues for the government, the y-axis represents the environmental damage. This is the negative of environmental damage, and therefore we are maximizing both. So we are maximizing the revenue of the government, and we are maximizing the negative of environmental damage. Now this is the Pareto optimal frontier which we obtained. Now if at all this represents a preferred region for the government, then what the government could do is, it could just set the taxes in such a way that the company would be forced to use this technology. A is equal to 2 represents the technology, and there are 4 technologies available. So just by choosing the taxes in a proper way, it would be such an optimal solution that the government would be forcing the company without directly saying that you have to choose this technology. Without saying that, just by adjusting the taxes, the company would be forced to choose this particular technology, and therefore the government would get the results what actually it is looking for. Now we did the simulation for 5 years, which are 5 different time periods, and what we observed was that the tax structure should go something like this. So it's more or less looks like linear over here, and that's how it is increasing. And this shows the quantity of metal produced. Of course, all these axes are normalized, therefore you should not look at it as percentage or maybe kilograms of gold or anything like that. They are all normalized. Now based on this, the information which we get is that the government should charge 75% as tax, and 25% of the amount should go to the company. Now of course this looks like a very high tax, but just take into account that the government is not charging anything else. It's like it owns the mine, it owns the gold, and it's inviting the company to come and extract the gold from there. 75% of the revenues goes to the government, 25% goes to the company. So that's one of the solutions which the government might go forward. Now here I'll show you a small simulation. Now again, this axis represents the revenues, and this axis represents the negative of environmental damage, and we are maximizing both the objectives. Now, we are using an evolutionary algorithm. It's a Bilevel algorithm which me and Professor Dave had developed in 2010, and that's the algorithm running at the background, and this basically goes and optimizes and gets the frontier. Now what it's doing is, it's optimizing the lower level problem at each point, and then finding the solution. And that's how it slowly, and then it also uses some principles from the multi-objective NSGA2 framework in order to converge towards the Pareto optimal frontier. Now of course I've added a delay in the program, that's why it's moving a bit slowly, so that you could visualize the way the frontier is moving. Otherwise this runs quite fast. Some other applications of Bilevel programming are maximizing production in chemical industries, which I already mentioned. And the second interesting thing would be defense applications like strategic, offensive, and defensive force structure design. So let's say if at all you want to go and attack with your with all your equipment somewhere, then if at all you want to maximize the damage caused to your enemy, then what you would like to do is you would like to optimize the enemy's problem as well. So you know that if at all you're attacking somewhere, the enemy would be reacting optimally. So if at all you take the enemy's problem into account and then you optimize your strategies in such a way so that you're able to cause the maximum damage, then that would be a Bilevel problem. Similarly, there is the strategic bomber force structure and allocation of tactical aircrafts to missions. So all of these would involve some sort of Bilevel programming in the background. Other applications also include optimal shape design, operating configuration, and optimal facility location. A facility location problem would be like you would like to set up a production factory somewhere. Now you want to determine the place where you should put it. Now, if at all we are putting it at a particular place, you would like to consider your competitors as well into account. And if at all I'm putting it in this state or this city, what kind of influence is it going to have on competitors? It might reduce the prices in that area, and there might be a number of other competitors in that area. So is it good to put it? Because if at all, as soon as you put up an industry or a factory somewhere, the competitors would like to optimize their own problem. So before setting up a factory, you should optimize your competitor's problem as well in order to find the optimal solution. Bilevel scenarios can also be found in nature. This is one of the slides we have, and we actually were discussing about this today, and we haven't really given it a lot of thought as to what exactly is an upper level variable here, what exactly is a lower level variable over here. But what we would realize is that if at all there is an alligator bird which is picking up some meat from the alligator's teeth. Now, the alligator could very well close the mouth and eat the bird, but it doesn't do that, because the bird is doing something good to it, right? But still the alligator is in the control, he's the leader, right? And the bird is also benefiting from it, and the bird is the follower. Similarly, in this example, if you see the bird sitting on top of a zebra, now the zebra could move its tail and just get rid of the birds, but it doesn't do that, because the birds are doing something good for the zebra, though at the same time it's also causing a bit of harm. So here I have a cleaner and a client benefit and cost table. So the benefits for the cleaner is that it's getting abundant source of food, but at the same time there is risk of predation. Similarly for the client, which is alligator in this case and the zebra over here, or a big fish in this case, the benefits are that the parasites are being removed and it leads to faster wound healing, but at the same time the birds might also be eating a bit of skin of the zebra, so there is loss of skin and of mucus and loss of foraging time, and it's more visible to the predators if at all it's just going around and waiting for the birds to come and sit on its back. Therefore, there is a leader, there is a follower, and there is a sense of bilevel optimization problem going on over here. So with this, I would just like to invite Pekka, Malo to take the presentation ahead, and I hope this gives a sense of it.
Thank you, Ankur, for providing the introduction to the topic. Given the time constraints, I'll try to be a bit quick. Though I'll be talking about an algorithm that we have recently developed, I'll try to keep the discussion at a fairly heuristic level with omitted all proofs and most of the technical details to make our best of the inclusion. Alright, so at the top we have the original formulation for the bilevel problem. Now, Ankur talked about a number of strategies which we might approach solving the problem. So now, to get towards one of those strategies, we like to rewrite this lower level optimization problem as a set value mapping. So, given a parameter x, it maps it to the set of optimal lower level decisions. Now, in order to move ahead, we asked that could we utilize the mapping psi in a somewhat clever manner that we could design a more efficient algorithm for solving this problem. So at this stage, both definitions are still just equivalent. We have just replaced this with the mapping psi. If the solution to the lower level problem is uniquely defined, then things are simple. This psi is just a function, just an ordinary function. But throughout, it's best to remember that there can be multiple optimal solutions, so we can never actually forget that it needs to be treated as a full set value mapping. Now, how our idea of using the psi proceeds. So actually, in this figure, we can think of the psi as the mapping that takes the points in the upper level variable space, the cloud, to these paraboloids on the lower level. So now, the question is that does the psi mapping have some properties that we could utilize? Now, in this figure, we have tried to illustrate this idea that if at all, on the upper level, we have two alternative decisions close to each other, then would it be so that also making a small perturbation here doesn't lead to a huge change on the lower level? So we might expect that actually the lower level paraboloids, they would be fairly close to to each other. And actually what we can show is that yes, the psi mapping indeed has such mathematical properties that make this approach possible. So we can show that in small areas it tends to be quite conveniently behaved, and we can make a nice use of it in the algorithm. So the whole approach, which is called Bleak, is the idea of using that mapping and approximating that mapping using an evolutionary algorithm so that we can make the algorithm proceed a bit faster so that we can avoid solving the problem, the lower level problem every time. So here's a flow chart of how the algorithm works. So essentially, it's the interesting stuff happens here. So we initialize the whole problem by producing a group of solutions which are fully optimal. Both the given upper level decisions, we have fully optimized the lower level problems, and we know that they are feasible solutions. Now based on this, we take a statistical approach. So we can approximate the psi mapping. So we make a lot of such local approximations for the mapping, and based on those, we can try to get an idea what the lower level solution would be without actually solving the problem. So clearly, by just calling that function, the psi function, we can get the value for the lower level problem. So it speeds up things a lot. Now, when we can proceed with that, of course we need to evaluate how good the fit of the psi function is when we are estimating it. If it's a really nice fit, then we can quite safely use it to produce no new lower level points. If the approximation turns out to be crappy, then of course we need to do the lower level optimization fully again. And so we continue. And now, as much as we can leverage the psi mapping, the more we can save time in evaluating the lower level problem. Now, why did we go for this evolutionary approach? Well, classical methods, they have a lot of constraints to them. They assume continuity, differentiability, and convexity. And these are not necessarily at all in problems what are encountered in practice. Furthermore, having the requirement of solving the lower level problem puts us kind of in the position where we need to solve the second order derivatives to even obtain a necessary condition. Furthermore, the psi mapping, though the mathematics shows that, well, the psi mapping has properties so that it would be nicely approximated, there isn't any kind of proper general results that would allow us to nicely compute the psi. So evolutionary approach provides a kind of a way that when we are generating the points, we can use statistical technique to obtain the psi mapping. So that helps. This idea of approximating wouldn't be used elsewhere, but it really is kind of a thing that works nicely with the evolutionary approach. Now, to be able to evaluate that do the algorithms perform nicely, we have taken quite a lot of efforts to create a unified test problem framework. So to be able to test all the properties that make up different types of bilevel problems, we have enlisted here desirable characteristics that the test problem should have. So when designing the framework, we would like to have ability to control the difficulty of convergence at both the upper and lower levels. And we also like to see that how the two levels interact with each other, and we'd like to be able to control the type of difficulty there is. Now, one thing is also the multiple global solutions at the lower level, which makes the problems certainly more difficult. So clearly we'd like the test problem framework to include a few such problems that enforce that in order to be able to build a good algorithm, it should be able to handle all such cases where also multiple global optimal solutions occur. Yet, to make the evaluation easy, we want that the relationship between the variables is clearly defined, so it makes the problems a lot more tractable, and to be a practical value, the problems need to be scalable. So that means we can increase and adjust the number of variables included in the test problems. One of the characteristics in bi-level problems is the existence of conflict or cooperation between the two levels. And it's important to be able to have both cases, because they actually having a conflict or cooperation adjust the type of difficulty the problem has. I would say that in the most proper bi-level problems, you tend to have both occurring at the same time, different areas of the problem. And definitely, to be able to evaluate the optimal solution needs to be known. So given these requirements, we have defined a test problem framework. We have made it, decomposed it into different parts. I won't go now into the details of this framework further, but we have taken there into account all the requirements enlisted on the previous page. So here's an illustration. Now, on the upper level, we have something that looks like a quadratic function. So fairly simple stuff there. But on the lower level, we have multimodality induced by Rastritchen function. So now how this looks like is that in the middle of this figure, we have contours given for the upper level function. And now we consider what happens at individual points. Remember, of course, that the global optimum is at point 0, 0. So now we pick 4 symmetric points here, and we see that when considering different points and comparing them to the optimum, we see that the landscape changes. If you pick up the points at different places, the landscape will, of course, differ once again. So we see here, when we examine the lower level contours, the effect of the multimodality. So there are many such problems we have designed, and they introduce quite difficult cases as well. Now, to be able to compare our algorithm, we have presented here results where we compare it against the nested approach. Like Ankur already described the nested approach as a case where you fully, even an upper level decision, you fully resolve the lower level optimization problem again. Now, what we observe in behavior of the algorithm is that on upper level we have considerably less function evaluations than at the lower level. But in comparison to a nested approach, we can generate considerable savings. So for the different types of problems, the savings with respect to the nested approach are given here. So how many more times the nested algorithm require function evaluations. So clearly, the use of the psi mapping idea, it helps a lot, and we have been able to achieve especially improvement in the lower level. That's what we expected to happen, since we are now using the psi to just quickly compute the lower level optimal solutions. Now, what the approximation looks like. So the true relation here, we focus at the point 0, 0. That's the point of interest where we want to be. So the true relation is given by the fixed line, fixed gray line, which runs here, and then the last approximation used is the black dots. So we see that around zero, the approximation we have constructed using the evolutionary algorithm, it follows this true relation very tightly. So actually, so it has worked quite nicely. Of course, we understand that if we move further away, then the quality of the approximation suffers. So you cannot push the use of such a technique too far. But in a close vicinity, things work nicely. Here we have also some convergence plots for the not the logarithmic scale, so for the evolutionary algorithm to verify that the problems have converged nicely. So these are the progress paths given for the elite members for the upper level and for the lower level. In addition to our own test problems, we have also made a comparison with the Wang et al. Algorithm, and obviously when we compare the number of function evaluations needed, here the sums are the sum of function evaluations of both the upper and lower level functions, and we see that the savings with respect to the algorithm presented previously by Wang et al. They're quite large. So at the moment, the Wang et al. Has been a kind of a reference point. There hasn't been much proposals since then, and that's the kind of gold standard against which we benchmark the performance of our algorithm. And the test problems here, the TP1 to TP8, are ones Wang et al. Had themselves collected from the literature. Now to conclude, bilevel problems, they have considerable interest for both theorists as well as practitioners, and clearly there is a lot of demand to improve the efficiency of the algorithms. Because otherwise, the practical problems, they tend to be very heavy, and there are time constraints as well for the decision makers, so we don't want to wait unnecessarily long times. Our approach is one of the few initial steps we have taken towards improving this, but there is obviously a lot of other tricks to do, and a lot of improvement can be done. Now, the advantage of the evolutionary techniques is that we are not restricted to overly simple problems, but we can treat, we can accommodate discreteness, we can consider nonlinear problems. All right. Thank you very much.
Okay. Okay, there are some times for questions. Anybody?
Yeah, I guess if I understand correctly, what you're doing is you have in Bleak, you should have a population of the upper level parameter, and each time you wanted to evaluate the upper level one, you used basically an estimate to guess where the lower level problem variable would go to. Have you tried, or do you think that it would be effective to use a fully coevolutionary system to try solving these sorts of problems where the upper and lower are two separate populations and they evolve against each other?
Well, the coevolution is an interesting question discussed with Ankur quite a bit, and actually one of the issues in the bilevel is that solving them is that the nested approach makes a natural sense in many cases, because the problems are kind of detached from each other. So establishing a coevolution between them, that's a kind of an ideal situation if you can make them nicely co-evolve with each other. But that's not easily done. That's very difficult. So if you can, that's what separates the kind of intelligent techniques from purely nested one. In purely nested, there isn't really any co-evolution. And now with the help of this mapping, we try to induce some of it there.
Actually, See, that was the first thing which we thought that should be an ideal algorithm. That there is a population which is converging at the upper level, and there is another population which is converging at the lower level, and the two populations are interacting with each other and slowly converging towards the true bilevel optimal solution. But the problem here is that if at all you have something from the upper level, and if at all you have something from the lower level, and you take it together, you cannot even evaluate the objective function at the upper level until and unless you know that it is an optimal solution at the lower level. Because if something from the lower level is non-optimal, you don't even know that how good it is at the upper level. So only when it gets optimal, then you get to know, okay, now I have a feasible member. Now I should be able to make some comparison with the upper level. So that's the difficulty of the bilevel optimization problem. That
If I may add a little bit to what they're saying, these problems are not symmetric. That means it's one way down. Like the upper level is more important than the lower level. So when you're thinking of co-evolution, usually the problems are symmetric. There are two problems. You can go this first and then that, you come back and forth. But here, the upper level controls the lower level. So unless you have a good enough solution for the lower level, it doesn't make sense at the upper level to take it and evaluate the upper level function level. So you can do co-evolution, but you have to change it really in its concept that you need to do more of one evolution and less of the other. Unless this is stabilized to close to its optima, you are introducing a lot of noise if you just try to evaluate it under
Or
the other.
then you end up being restricted to a certain class of problems where the co-evolution works. So if you make a strong assumption and that all right, we are not interested in any kind in all types of problems, but we want to make the algorithm specialized, then of course you can achieve more. But in a fully generic setup, what we have tried to strive for is it's very difficult to achieve that. And to make a difference between a nested approach, that's a real challenge.
But it's an interesting thought, and something can be done also
Good.
in that direction. Yeah, go ahead.
Question from Idaho.
Yeah, go ahead.
Question from Idaho. Speaking about specific classes of problems, I was really intrigued by your using these techniques to make policy recommendations. Because one of the things we know in modern economic theory is that you don't have perfect information and you don't have perfect rationality, but both of those are bounded. And it seems to me that your setup could be used really nicely in an imperfect information and bounded rationality framework that might be even more applicable to policy recommendations than what you've got. And have you thought about incorporating those relaxations of information and rationality?
That would certainly be interesting. The steps we have now taken towards the applied ones are very preliminary. We have just considered a couple of problems like the mining problem, so forth, but definitely this will be interesting for the future work.
I mean, both of them are from business schools, so it makes sense for them to take it up. I think that's what you're saying.
I think it'd be a thing to do too, because the way you're evaluating, the way you're estimating psi, you could incorporate bounded rationality and imperfect information almost just by throwing in some noise. So it'd be a really good thing to do.
Excellent suggestion, yeah. There was another question for you. Correct? Yes, okay.
So I was curious as far as applications, if you thought about this kind of approach could work in like wildlife management or something like that, you know, control of I don't know, invasive species or other things and how the other species in that environment would react.
Yeah.
Is that something you consider?
So it goes similar to his suggestion about policy management. So
Right,
just
yeah, I
do
guess
it
it's
in
just
any
different.
area. Yeah.
Okay.
Great suggestions, yes.
Right, so whenever the thing is that whenever you have some kind of a hierarchy where you are able to identify the leader and then a lower level thing which could be a follower, then the approach just becomes applicable over there.
I guess it should be summarized by considering three criteria. So you have two layers of decision makers. There is an interaction going both directions between them, and at some stages you have conflict, and most likely both cooperation and conflict in the same problem. So if you just have cooperation of just, then I would not really call it, consider it as a kind of a strong bilevel problem. Interesting, it could be formulated as such, but it doesn't necessarily require going to such algorithm. There might be much more efficient ways to approach.
And one another thing is that these problems are very common in real life as well. So today we were discussing an example that if at all in a company situation, you are a boss and you have a subordinate. So you want your subordinate to work optimally, and therefore you might show some kind of a bossy attitude. If you are probably too bossy, the employee would quit, right? If you are too little bossy, then maybe the employee would be slacking off and not doing the work properly. So you need to optimize your own problem with respect to your employee's optimization problem. So you want to determine the bossiness attitude in which your employee would be operating optimally in your favor. So even that's a leader and follower problem.
Any other question?
Question from Washington.
Okay, first the question from Washington. Yeah, go ahead.
Yeah, so I'm just curious about whether one could extend these to tri-level or n-level problems. It seems like in cases where, for instance, the government sets a tax, a company then responds to it, the clients of that company respond to that. Are these techniques sort of readily deployed for n-level problems? Do n-level problems come up?
Yes.
How much savings do you get when you start extending the hierarchy?
Right. So
At the moment, we haven't evaluated that.
yeah, we haven't evaluated multi-level problems, though multi-level problems exist, and I have one example in my mind right now. So the thing is that if at all you imagine a couple of companies which are, and a third individual which is a government. So if at all there is a government, a company which could be some kind of a steel company which is operating at a upstream next to the river, and there is a fishery located downstream in the river, then the steel company is polluting the river, and that's influencing the fishery which is located downstream. So here we see a three-level hierarchy. The government is there, which would like both the companies to survive. Then at the second level, you have the steel company which is trying to optimize its own profit. And then at the third level, there is the fishery, which would try to optimize its own profit, but of course it needs to take into account that the steel company is polluting the river. So there is a three-level hierarchy over here, and similarly you can come up with more examples where you can have n-level and multi-level hierarchy. But yeah, mathematicians do talk about multi-level problems, but the mathematics just gets tougher and tougher because you get higher order derivatives in the necessary conditions.
Yeah.
Do you think the benefits of these techniques are going to accelerate as you go to higher levels?
Well, it depends how the problem is. If the problem is a higher level problem, then of course you need to have first of all a technique which is able to handle it, right? And right now we are struggling to solve bi-level or two-level problems. Once we are through with it, then maybe we'll try to go to the next level. But yeah, it becomes computationally very expensive as the levels increase.
And whenever one adds a new level, one needs to think carefully that is it really requiring truly the new hierarchy, or is it more like that you're still, say for instance in the mining problem, one might think that, let's introduce a third entity, a holiday resort that operates in the area. Now, if the holiday resort would depend on the decision of mining company. If the mining company decides to go for huge quantities and it rigs up the whole area, it doesn't make much sense to do business there anymore. So it might want to adjust the extent of its operations and investments according to the behavior of the mine. But now, then again, this is not really a tri-level. This still remains as a bi-level problem because the resort cannot affect the decisions of the mine. The mine will do whatever it wants. Once the government has given it the permission, it will do what it likes.
We have a question from Idaho. Do you still have the question?
Well, actually, it wasn't a question, just an idea. It occurred to me that this doesn't have to be optimization, it doesn't have to be economics. This might be an interesting model for things like passenger-driver succession models in ecology, where you've got complicated ecological succession rules that aren't entirely predictable because someone gets there first. So it was just an idea that you might be able to use this to model succession rules in ecosystems as well. Nothing really concrete, no real question. Or biofilms. I was actually thinking of the human microbiome where you've got discrete but a small number of different microbiomes associated with healthy conditions. And it could be that the difference is whoever plays first gets to determine how the ecosystem develops. And I don't know that there's been any really good modeling of that passenger-driver ecosystem succession models. This seemed like it might be a framework that you could do some simulations in.
Yeah.
Nice work, by the way.
Thank you. Okay. Any other questions, comments? All right, then let us thank both the speakers once again.
It's useful for these assumptions. I think that he really wants to
Okay, yeah, that's just wanted to make sure, because I was like, if your estimator and your problem match, now kind of like,
我不知道，这感觉很奇怪，它的第一层还都是projective。
这好神奇啊 She sounds like she knows how to do it. She said it's easy, so I was like, okay, well then, we just want to workshop on it.
Yeah, I think it would be good, and hopefully, like, I know that we're kind of like almost time, but like, at some point there's something. But generally useful, I think people would really like.
I hope people understand it.
To do outreach in a way that fits their schedule. Like, I do Twitter outreaches.